I'd like to start off tonight's event with a beautiful introduction from two exceptional speakers we have with us tonight. We have Sergei Tsarev. He is the co-founder and CTO of Clustrix. Prior to Clustrix, he led AOL's Internet Operations System Infrastructure team, where he developed a high-performance data storage engine that has become AOL's standard storage engine for network and host operations. Guys, you made the database for AOL. We also have Dmitri Mikhailov, who is the principal database architect for TheLadders. He's got over 20 years of big data experience. Works in global 500 companies around the world. Thank you, both of you guys. Welcome to have you guys.
Thank you.
What? Oh.
Actually, can we get the lights so we can read with the projector? Alright, so we'll get started. So, as I introduced me, I'm Sergei, one of the founders of Clustrix. The other one is actually Paul myself. Before that, Paul started a company called Isilon Systems that a couple of years ago got sold to AEC for $2.4 billion after going public. So that was a pretty good exit for him. So I'll just talk a little bit about Clustrix, what we do, why we started this whole thing in the first place. And you can read, Clustrix is scalable distributed database built for the cloud. And we have a whole bunch of ways to deliver the product. We started off as an appliance, so you would buy hardware from us. It came loaded with the software, and it has some high-performance components in it, like InfiniBand and solid-state drives. But it's really kind of a high-end solution for folks that are really struggling with database scalability. We also have a couple of other ways to deliver the product. We recently launched a decoupled software offering on AWS. So you can actually build out a scalable distributed database using just regular AWS instances. You can also get the product from us as a service. So we run some hosted infrastructure that's based on our appliance. And later this summer, we'll actually have downloadable software as well. So I won't go too much into why scalable databases. It seems like these days most people get it, right? You have growing data sets, you have tons of concurrency, you have pretty complex SQL that you're trying to get value out of the data that you have in the database. And traditional databases simply don't scale, they don't meet the challenge anymore, right? You have, whether you have too many users or just you're collecting too much data, generally it overwhelms a single instance database, and you have to do something to solve this problem. So the first sort of way that people try to do this to scale up, they either try to get bigger hardware, so they get more and more exotic types of hardware, like Sun Microsystems, or high-end storage arrays like EMC Symmetrics or 3-part or whatever have you. But the problem with that is that eventually it stops working for you, and it gets very, very expensive. So, for example, if you took a company like Facebook or Google, there's no database in the world that can run on a single instance machine that can accommodate all of Facebook's data set. That database simply doesn't exist, right? So they have to solve the problem in another way. So how do most folks do it today? They do it through sharding. So they figure out how to split up their data sets into smaller database instances, and they teach their application how to query these individual database instances and really kind of push the problem back up the stack. So now the application has to do some of the work that a database used to do for you. If you have some complex query that's looking across a large set of data that exists in multiple databases in your infrastructure, well, that's not something that your database is going to resolve for you. That's application logic that you now have to write and maintain. So it comes with a whole bunch of problems, including the upfront engineering and also maintenance of sharding. And something that's been pretty hot these days is also NoSQL. It's sort of another way of looking at sharding, is really reducing what the database can do for you and simplifying the query language and the interface and kind of going the NoSQL route. Some of the NoSQL databases are actually getting more sophisticated, and I would argue that they're starting to approach the complexity of a SQL interface as well. So they're sort of re-implementing the wheel there. So, what is Clustrix? Clustrix is actually a scalable distributed database that's built on top of commodity hardware. So you have, it runs on pizza boxes, right, Intel boxes. You load up the software and you get one single instance database out of it. It's actually ACID compliant, so we're fully transactional. We look like a single instance consistent database, but you can read and write from any of the nodes. We're also MySQL compatible, so if you have a MySQL application, you can just drop us in and start using it without having to rewrite all of your SQL queries and application logic. And let's just point out that there's no MySQL code in the product. It's something that we build from the ground up, from scratch, and so we're not beholden to Oracle for their code base. We also have built-in fault tolerance, and I'll show you a little bit more about the architecture and how we handle that. But if a node dies, for example, the database will automatically reprotect itself. You don't have to do anything. If you want to expand the cluster, you simply add more nodes. You say, here's some more resources for you. The database will automatically redistribute your data set, and you will suddenly have more transactional capacity as well. And I think the one thing that's really different from some of the other distributed SQL systems out there is that we handle a very wide variety of workloads. So it's not just focused on the high-scale transactions. For example, you look at something like MySQL cluster, which we get asked about a lot, and you say, well, how are you different from MySQL cluster? If you look at MySQL cluster, they're designed for a very specific workload in mind. It's an in-memory database. They do very, very well on kind of key value transaction model. But as soon as you start adding more complex queries or large data sets, that's just something that they don't do very well on, right? So if you want to have an aggregate query that's looking across millions of rows, that's not something that MySQL cluster will help you scale. Or if you're looking at some query that has some complex join logic in it, that's something that MySQL cluster is not going to do very well on. So one of the things that Clustrix does is actually we have a fully distributed query evaluation engine, which allows us to also do the analytics style workloads on the system as well. So not only can you do the high scale transaction, lots of little queries updating rows, heavy write traffic, heavy read traffic, but also the kinds of queries you start getting as your business starts to scale and you want to get more insight into the data. And you start running things like nightly reports, right? And these are usually complex queries that are looking at millions to billions of rows. And you need to get some sort of summary of your business activity on the real-time system. And usually what happens is your operational database, or kind of the database that's running your back-end application, is incapable of processing those kinds of queries. At first you start running those queries off-peak at night, but then your business folks say, well, I want to get the answer now while I'm at work during the day. How do I do this? And what ends up happening is you usually build a whole new system that's doing the analytics for you. And now you have two databases, and you have multiple DBAs, and you set up some sort of a pipeline that takes data from your transactional system into your analytics system, and it's complexity, right? So these are some of our customers in different market segments. One of the interesting market segments that's becoming hotter and hotter for us, I didn't have a chance to update this slide, but there's something like 5 or 6 different logos there, is advertising analytics and sort of ad tech in general. Because those guys, there's a lot of interesting companies that are coming up in this space now, and they're really pushing the envelope in terms of the right throughput that they're getting out of every ad impression is right to the database. Every ad show is a hit on the database, but they're also trying to hone in who is viewing which ad, so everything is becoming more and more personalized. So, for example, if a person is trying to get the most bang for their buck in terms of the audience for which ads they show, you want to know. It's like, oh well, this guy is coming from the Lower East Side. We're on a dating website. He's looking for this kind of person. This is the kind of ad that I want to show this person, right? Maybe some Venmo ad or something else, whatever it is that You do updates when you go on Lori's side. I guess it's all about cars, right? Dmitri, what's your favorite car? What was that? He has many. Dmitri's a popular guy. So just a couple data points on showing that we can really scale well for both kinds of transaction loads. On the left side is really showing kind of the transactional problem. This is a chart for a dating company in Europe. And what's interesting is that they grew very, very fast. It's by a company called Massive Media, and in early 2000s they started a social network that became very popular in Europe, and they developed a huge infrastructure, about 100 different MySQL servers, sharded servers. And when Facebook came to Europe, it essentially decimated their market share. Facebook just took over that market, and they said, okay, well, we know how to build a web app, we know how to build audiences, let's build something new. So they decided to build a dating website, and they were able to cross-promote the dating website on the social network, and they got astronomical growth. Like within the first 3 months, they were able to get to 1 million users essentially, which was pretty cool. But the problem is that they built the whole thing on top of a pretty beefy MySQL database, but one, they didn't really want to shard because they've done it before, and two, sharding is actually a difficult problem to solve for a dating website because you have to figure out how to partition your data set. But in dating, it's a fundamentally relational problem, right? You're trying to figure out how different users are associated with different other users across multiple preference domains. So figuring out how to break up that kind of data set becomes a very challenging problem, so they didn't want to do it because it would mean that instead of experiencing this high growth that they would have to pause and do a bunch of engineering to figure out how to shard. So they started with a 3-node Clustrix cluster that they were just experimenting with. They didn't think that they would hit this kind of a massive growth curve so fast, and were simply set up as a slave to their system. And one week we get an email from them that says, congratulations guys, you're in production. What ended up happening is that their MySQL server fell over during a peak. They just had an unprecedented number of new user signups, and they really had two choices. Either they're turning users away to try to prop their site up, or they switch to Clustrix and see what happens. They switched to Clustrix, they never looked back. So throughout the couple of years that they've had us, they've had multiple expansions. This last expansion is up to 15 nodes, and this summer they're putting in another order for a larger cluster because they're continuing to grow. And this is a system that I think now it's pretty close to 100,000 transactions a second. And these are not simple key value lookup queries. This is actually an interesting workload. It includes aggregate queries, it includes joins, it includes sort of the kinds of things that you would see in an app. And on the right-hand side, there's just more of a this benchmark that we put in-house to show that you can scale a more complex query as well. So this was an aggregate query that we ran on a system that went from 3 nodes all the way up to 32 nodes to show that we have linear scalability for complex queries as well.
How do things scale on a traditional MySQL server?
I'm sorry, how does things scale?
How does that scale compare to the scaling you see on MySQL server?
Well, it doesn't, because the x-axis on that display is number of nodes. You can't add nodes to a traditional MySQL server, right? Unless you go the sharding route.
Right, so
in that case, how do you do a single query that spans the sharded MySQL infrastructure? Right, I mean, sharding is really re-implementing portions of the database inside of your application, right? I used to have a bunch of animated slides to show the architecture, and we're in the middle of creating an interactive way to show the architecture. So I have a prototype video that I want to share with you guys. It's not fully baked, but it starts off as sort of a good way to show what the product does, or how it works rather. So the idea is that you start out with one large table. Let's say that you have a table that has billions and billions of rows. Let's say you're a photo sharing website. You'll have billions of photos that you're cataloging, and usually you have pointers about the photos in your database, right? So if you're building this in AWS, for example, you usually have a relational database that keeps track of who owns all the photos, who can view the photos, right? Who various permissions issues, things like that. And there'll be pointers to the file system to something like S3. So this single table is simply too large to comfortably fit into even the largest instance that you can get, for example. So what do? Clustrix takes a table like this, splits it up into smaller chunks that we call slices, and then distributes these slices across the nodes in your cluster. Now what happens if you want to add a new node? The system automatically ingests the node into the cluster and redistributes your data set. So all of these operations are completely automated. You don't, as a DBA, you don't need to do anything. Sorry, I'm going to move it a little bit further. Too much feedback. And can you guys, is this clear? Can you guys actually see this?
I have a question. What you're basically saying is that the relational model isn't working, and you're going back to a network topology and trying to make it, because you're basically having indexes that are doing the work, and you're still telling people it's a relational table.
Well, what I'm saying is that the relational model is now broken, and it is working, but the way that we used to build relational databases is broken. Right? So a single instance database is not good enough anymore.
I will agree that, but why, if you have something that has so many rows and you have so many relations, so many things pointing to it, why would it have been put in all those tables to begin with is beyond me.
That's one table. That's one
It's one table.
Yeah, well, even one table makes it even scarier. Yeah.
Well, I'm sorry, what's the alternative?
I'm going to sound like an old fart. There was a database thing called IDMS, that's what we would have done. We would have just created nodes and would have pointed to it and then traversed it pretty fast.
Right, so you can make things, I did another talk at one of the Procoding conferences about the history of the database. And yeah, you can go back and trace the roots of, people used to build their own databases, and the database and the application were the same thing. And then you have the next step of saying, okay, well, I'll have the storage engine. Everybody's building the same B tree. Let's make a B tree library. And then you say, well, everybody for their B tree is trying to make it transactional. Well, let's make a transactional B tree that's embedded, right? So things like Berkeley DB came around. And so over time, as you're trying to get more and more value out of your data, you want to have a high-level language that exists for the database that you can query against your data set. And you want it to be reasonably powerful because you don't want a programmer to be able to be the only one who's actually able to get any value out of the data set. Right? So this is part of the issue that we see now with technologies that are traditionally NoSQL like Hadoop, is that, well, how do you get value out of that data? You have to go hire a programmer who understands Hadoop, who understands your data model, in order to be able to give you access to the business intelligence from the data set. And now a lot of the Hadoop companies are actually putting a SQL interface on top of that because, well, hey, you want a declarative language that's actually reasonably powerful to give you these answers. You don't want to sit there and manually code how you're going to get at all these queries. So the idea with Clustrix is, yes, we're applying a shared nothing architecture, right? This kind of massively parallel distributed processing at this problem, but on the front end, you still have the relational model that really works, right?
No, I'm not arguing that point. I'm just saying it seems like you start off with a more complex. Never mind.
Well, this is all hidden from you, right? So this is the relational model that works for you for a 100-row table. Why shouldn't it work for a 10 billion row table?
Because I don't think the relational model was designed for a billion row table. That's just my personal opinion.
Okay.
I don't see it so far when I'm hearing it.
Mm-hmm.
Just price-wise, it's different.
So those guys, we can get into real kind of minute differences of DB2. Like those guys co-locate indices. They don't handle necessarily a wide range of workloads. So which big internet company uses DB2, right? It's not only price.
Well, hello, but the Federal Reserve does.
Okay.
And if you don't get your money tomorrow when you go to the ATM, you'll be more upset if the Federal Reserve doesn't give you your money than if an internet company
Yeah, but
does.
okay. So so Rakuten is one of our biggest customers. So Rakuten, the amount of sales volume that they do is 5% of the Japanese GDP, and for that they use Oracle. And you know what? They'll never use Clustrix, at least not in the foreseeable future. And why? They use this very specific version of Oracle. It's very tightly regulated. For them to even do a patch update to Oracle requires getting permission, right? It's a long process. So yeah, so there's a lot of those kind of older database systems that exist in the world that collect quite a bit of revenue, and they're embedded in there only because it's almost impossible to.
But they also work.
They work for that problem, but they don't work for everything.
From a logical perspective, it looks like partitioning. It looks like standard disk partitioning, but of CPU resources.
And across nodes.
Do you get to pick how it's partitioned, or does it just intelligently do it? And if so, how?
Yeah, so it's partitioned. It's a consistent hashing model. The database decides how to partition the data for you based on the index keys that you specify. And you can hint the database to what you want it to do. So if you thought that it made the wrong kind of distribution choice, you can actually tell it to make a different kind of distribution choice.
Can you re-index on the fly?
Yes. Support online extensions. The question was, how are we different from VoltDB? So VoltDB is a memory database. The programming model is quite limited. You have to essentially write things in Java with stored procedures. And there's a whole bunch of other limitations on VoltDB. But fundamentally, it's the kinds of workloads that they support are very limited now. Yeah, so the distribution here is one of the kind of the key differences between us and most other systems is that we have independent distributions down to the index level. So, for example, in this, this is a simplified view, but you guys, it sounds like you want to get pretty deep, which I'm happy to do. So for most databases, you choose a single distribution key. So you can say, okay, well, I have this 10 billion row table. I want to partition it or distribute it based on the primary key. Well, what happens to all your indices, right? So for a particular partition, the data that's contained on this partition, all the secondary indices are co-located or they exist in that partition. So if I want to do a lookup that's by secondary index, I have to go to all the partitions and say, do you have this data? Because my data is fundamentally, it's just like the sharding model. It's split across a single key. So in Clustrix, that's fundamentally different. We actually have independent distributions for tables and indices. And almost nobody else does this.
So you have an index of the index.
Yeah. Well, this video doesn't get quite that deep. But essentially, and by the way, all of this stuff is actually written up on docs.clustrix.com. So, there are pages and pages explaining how the distribution model works and why we chose to do what we chose to do.
Well, there's a huge amount of work. It's a kind of application. If you want to deal with all different kinds of scenarios, you need to analyze, because you deal with different customers. Maybe have different number of tables, different table structures. You also distribute to maybe different number of servers and scales. You have to do all the, and also you're talking about different software like MySQL, Oracle, different database. But this analysis, this process could be a huge amount of work.
I didn't quite catch the question.
Well, you like using you build another layer for application. That will be.
We didn't build another layer. We built a new database.
Still the database.
All of this is a new database built from the ground up. There's no like MySQL in here that we built some layer on top of. This is our database. We take a SQL query and we break it into query fragments. There is a planner compiler that actually produces x86 machine code for queries that know how to evaluate themselves in the cluster. So it depends for what kind of model you're talking about. So if you have a high transactional load and you just want to make sure that the front end for query distribution gets assigned to different nodes, you can use a regular layer for a load balancer. In fact, the cluster comes with built in. So any node can accept reads and writes from any of the from any application connection. And for complex queries, what actually ends up happening, which I'll show you guys later, I didn't have that part of the video. I have some diagrams for a video that's coming. But we have a completely distributed evaluation model, so you can have lots of nodes in the system participating to do complex query resolution. So for example, if you're doing an aggregate, then you have lots of nodes participating in the computation of that aggregate.
Do you have like a control node or something? Or is it like everything is equal? All nodes are equal parity, or any one node is like a control node or
If
something?
they're all peers, they're all equal, and you know you can do your job like any node.
Can we add, can we add a node dynamically anytime, or we have to have like a term?
That's what this animation was doing. Is we're actually adding a node dynamically, and it redistributes the data for you.
So how much do we see any performance degradation when we are doing that one?
Yes, there's a performance penalty to that. It's usually in a few percentage points, so you have to provision your system to allow that kind of operation to happen. Fundamentally, you still have to move all the data within the cluster, so and you have to read it that causes cache effects. Hold on, there's a question behind.
You said like it plays nice with MySQL. Let's say I have like pre-existing aggregate function written in MySQL. How would it like integrate with Clustrix?
Oh, you guys, you mean you actually wrote some user-defined functions that are implemented in C in MySQL?
No, MySQL. Just like complex like queries in MySQL that I wouldn't want to rewrite. Let's say.
Yeah, I mean that's why we chose to go this painful route of actually emulating another database. It's plug-in, and Dmitri will talk about it later. Where they had something like with like thousands and thousands of different MySQL queries, some of them pages long, that just worked on Clustrix.
So how do you do the change, like translate to more native database?
Yeah, what ends up happening is internally the SQL query comes in, we have an internal intermediate representation for the query, and that's what the planner operates on. When the planner outputs a plan, we have a compiler that takes this representation and compiles it all the way down to machine code.
You talk about lots of rows and aggregating and doing complex queries. What about just pulling back a single transaction?
No, maybe we'll look at the video. Some of that stuff is covered. So this is just covering what happens when a node fails. So this is kind of interesting. This is not a master-slave model. All the nodes share the data amongst themselves. So for example, if you have a 10-node cluster and a node fails, you'll have 9 nodes that all talk to each other to reprotect the data set because they all hold some small portion of the data set. It's not like that failed node had an exact image somewhere else. So the very nice thing about that is as you start growing your cluster, a node failure takes faster and faster to reprotect from. So a 3-node cluster, let's say if it reprotects itself in 20 minutes after a node failure, 30-node cluster is going to reprotect itself in seconds after a node failure. And here's an example of a write query. So what ends up happening is a write query comes in, we decide which nodes actually own those rows. In this case, we color-coded them, and we have some green cards, so those are green rows that need to be written in the system. That node is going to know where in the cluster the rows need to go, and will in parallel go and do the writes. So in this case, for a simple write query, you can actually that those sets of rows go to two distinct nodes. You can actually have more copies of the data if you want. That's configurable down to an index level. So you can, for example, say, well, I really care about the data in this table. I want to have 4 copies of everything and 5 copies of everything. But you know what? The indices can be rebuilt. So in the event of a disaster where I lose 2 nodes at the same time and I lost 2 copies of data on an index, well, that's okay because my primary table actually still has the data and I can go rebuild that index. So we have that kind of flexibility. And in terms of the evaluation model, it's really bringing the query to the data as opposed to trying to backhaul the data to a central processing node. So in this case, if I want to get a couple rows and do some computation on them and return that, what's going to happen is that some node fields the query and sees that, oh, it doesn't have that particular data set. It's going to create a query fragment that knows how to forward itself to another node, fetch those rows, do whatever computation that needs to happen on those rows, and return the data set back.
So, depending on manage cross-platform queries, like different partition tables, you have like filters on one node and another node.
Yeah. I'll rephrase the question, right? What happens when you have more complex queries with things like joins and you're trying to relate those rows? And that's exactly what the system does. It knows how to do that, and it will manage that traffic flow for you. So if you have a complex join, you'll actually have many nodes within the system talking to each other to do that join operation. Again, the big difference, for example, with other technologies, let's take MySQL cluster again, and other databases do this too, is, well, MySQL cluster, they distribute the data similarly like this, but then what happens if you're trying to do a join? Well, only one node can do the processing for a join. So all the rows that are relevant for that particular join get forwarded to a single node in the system. It becomes a computational bottleneck. Within Clustrix, you have many nodes talking to many other nodes to actually do the join. So you can scale join performance by adding nodes.
But do you see in a case that you cannot really translate the SQL screen from one, like MySQL, to another, maybe like Oracle or just MS SQL? You cannot find the equivalent functions. Do you find it? Because different databases, they have different screen. Maybe in MySQL, there's one thing it does exactly well, but you cannot find an equivalent function.
Do you have an example?
Well, there's, if you go to like SQL cookbook, they talk about different database. For the same type of function, some database they could do it, some of them cannot do it.
Okay, well, it's a little too abstract for me because I'd like to talk about specifics. I can talk about what MySQL does because I understand it, and I can talk about what Clustrix does.
But in the SQL cookbook, right, there's many cases in which, for example, Oracle has a function, but you cannot find the same function in MySQL or in another type, MS. There's many cases, not just one. There's many cases, one function you find in one database, but there's no equivalent in another database. Then you would find a problem. You have to translate.
So maybe that Oracle application is not a good use case for Clustrix. I mean, I'm not sure what to say there, right?
Well, I think there could be a lot of things.
I'm talking about the general approach to solving this problem, which is a massively parallel evaluation model, which Oracle doesn't have, right? MySQL doesn't have, Clustrix has, right? So if there's some particular feature that's needed, some aggregate function, that's something that we can implement in Clustrix to leverage this kind of architecture, right? Where you have many nodes working in a query at the same time, which is something that those systems can't do. So the database, it runs on Linux. It's Linux, and it's Intel architecture. Red Hat. We don't support recursive queries.
What was
You
the
mean
question?
like Oracle Connect by?
No, I mean SQL with state.
Common table expressions.
And then it's
Common table.
they don't have.
We don't have everything that MySQL has, and we have some things that MySQL doesn't have. So it's there's similar routes.
Go back on the join. You were giving an example. Somewhere once that join is taking place, it sits somewhere. Is it in a cache of some sort, or where does that? Is it on a node? Is it where does the actual join take place?
Well, it's a pretty complex. That's a pretty complex question, right? How does join processing actually work? And it is documented on the website, and we can talk about it after this presentation. But the short answer is it takes place on multiple nodes in the cluster. So there's no one node that's actually processing the join. Multiple nodes are processing the join.
Then doesn't the result from the multiple nodes have to be?
Yeah, at some point you have to combine it. Of course, right? You have to combine the stream. The same thing with an aggregate query, right? So usually what ends up happening is you have a 10 billion row table, you run some sort of an aggregate query, it produces something like 10,000 rows because you want to have a result set that's actually meaningful that you can do something with. So each node is going to operate on a subset, right? If you have a 10 node cluster, 10 billion row table, each node is going to own a billion rows. That node is operating against a billion rows, reducing it down to 1,000 rows, doing that aggregate computation. Then those 1,000 rows are combined at essentially building the aggregate.
I think we're confused because you said that your software can find the exact node where things are joined. So I think that's why we're kind of...
No, I said that the software can find the exact node where things live, not necessarily where they join.
Guys, for the sake of time, we have QA at the end. Just kind of hold the questions a little bit longer, and let's just move on with the presentation, and we'll come back to Q&A. Everyone will have a chance.
Yeah, you guys are grilling me pretty hard on the technology, but I'll leave you the guy that actually, one of the guys that bought it, and he can go through why they bought it and whether it worked for them or not. So then you can judge for yourselves whether I'm full of shit or not. Right? Because honestly, you guys are telling me you don't believe that it works, right? And it doesn't matter what I say.
No, we
why don't we give the microphone to the guy that actually paid us money for this thing and is running production loads?
We don't understand you.
Why don't I give Dmitri a minute? You finished with the presentation?
Yeah.
No problem. All right, let's get to the ground. Previous page was essentially about the ladders. Everybody knows what the ladders is, who we are. We help people to find jobs. Business seems very simple. We work with job seekers, we work with recruiters. We have jobs posted by recruiters and applied. Yes, thank you. And job seekers apply for the jobs. So we have tons of logic behind the scene when we do matching, we run recommendation algorithms, searches. We run mail campaigns in order to engage our audience. So what's behind the scenes? Legacy database profile. This is where we started actually looking for scalable database solution. At that moment, we were running a typical master-slave MySQL topology. Master database, pretty powerful, 128 gig RAM. We had 16 slaves, half a RAM for master. We had 0.6 terabytes data per database, master or slave, 10 total. We used to keep our SAN in the back. It's a damn slow thing. Production applications, websites, admin tools, were Java applications running on around 20 nodes. Now we have about 50. Running on the Tomcat application service. Use different MySQL APIs. We had a lot of database tables. We had over 1,000 tables, 9,000 columns, and over 3,000 indexes. We had our database layer was pretty thick. It's 200,000 lines of SQL code. Why? Because we try to say SQL as fourth generation language. 20 lines in scale equal probably 200 lines of third generation language written in 3GL. So in order to speed up and make time to market faster, we simply extensively use scale. Query is pretty complex. So customer base at that point was 6.7 million accounts. We had about 4 billion rows of active data. Complexity of queries, this is actually traffic. 70% of our queries were short range or primary key lookups up to 200 million raw tables. We had 30% of traffic were queries with multiple joins from 2 to 7, up to 40 million raw tables. We extensively use force index, optimizer hint, because optimizer sometimes get confused. Falls in the logic that determines the calculated functionality of index. We used about 20% of queries had subselects on about 1,000 row data sets. And we had very complex analytical workload queries on 10 million raw data sets, but not too many. So we had tons of data, and we had problems on 3 fronts. So, we had concurrency problems, we have availability problems, and we had problems with large data sets. So data couldn't fit in memory. So the goal was to scale system smoothly and economically as requirements increase. We considered sharding, MySQL sharding. Actually, we did some estimates to find out how big the project is. It was pretty big. We considered NoSQL solutions, but with NoSQL we would have to rewrite the same way as if we go the sharding way, our database access layer to move joins and merges and sorts to the application side, which would be very expensive. Regarding databases such as big S&P boxes running Oracle in it or something like that, it's just a price for self-activity we didn't look at. And new cluster databases started popping up at that time. So that was very attractive. All right, so Oracle RAC, costly, licensing unattractive, scalability is sublinear, 25 node clusters, as far as I know, don't perform well. If you add 46 node, you cannot get your 4% improvement. But allows online schema shapes. ScaleDB, which you beta tested, was storage agent for MySQL. Used Oracle RAC architecture, used shared disk architecture. However, it suffered from the same problems Oracle did. Oracle RAC did. Unable to scale over a certain amount of nodes. Just because the chatter between nodes and the transaction manager was too high. But it was compatible with MySQL. This is why we looked at it. So we were beta testers of this product, and unfortunately, this solution is still in beta, or maybe fortunately. We looked at MySQL cluster. Price was good. People were running business transactions on it. It's a proven technology. However, as we had a lot of queries with joins, join performance was really bad in 2010. It has improved since then. I believe a year ago, version 7.2 came out, and they claimed that they improved join performance by 70 times. You can imagine how bad it was before. So we didn't look much longer and looked at VolDB. VolDB we'll have to rewrite our database access layer to Java store procedures, which would be very expensive. We decided not to go there. Clustrix, that's something that actually we liked immediately because we wouldn't have to do anything at all. Just plug it in, attach to the master, MySQL master, import data, set up application, promote to master, and start moving the load from the slaves. That's precisely what we did. No sharding, highly available. We would do online schema changes, so DB wouldn't have to wake up at 3 in the morning on Saturday to do the job. So we did some tests. So the blue line here is MySQL single box MySQL performance. This is write throughput, this is read throughput. Write throughput, just to compare, it was pure write test. Read throughput, we replayed our production traffic, about 500,000 queries, we replayed it repeatedly. This is log to log base 2 scale, so the right side is 16,000 connections, concurrent users, and you can see that when MySQL was dead, Clustrix was still performing very well. So that was something that I never seen before, and I love it. So let's take a look at what we saved. So the price we paid for final cluster was 150K, very cheap. Recurrent support, 15% of this price. Benefits, we saved CapEx. So our database setup, pre-Clustrix setup was about $500,000. So we repurposed, reclaimed our servers and repurposed storage, saved about 420,000. So, yeah, we'll get there. $420,000. So we eliminated the need of sharding data. So this is from a sharding project evaluation. We would have to spend $250,000 for initial code rewrite and about $100K a year for support and maintenance and ongoing development, of course. So we eliminated a single box memory limit. We wouldn't have to upgrade our servers. Plug in, stick more condensed memory and such. So we got non-disruptive online deployments and schema updates. Just something to look for. We had 10 maintenance windows in 2010 and 18 hours of hardness of downtimes. It's a lot of downtimes. We eliminated MySQL single master database, single point of failure master database. We had issues with master database when entire business stopped for 2 hours. We eliminated write concurrency bottleneck. We had a lot of connection pool insertion cases with connection pools on the application side, and we had to fix data after that because transactions, we don't use transactions fixes atomic, and we have to fix data, bring to consistent data. We eliminated write bottleneck introduced by a single threaded MySQL application because there is no application anymore. And like it or not, but the solution eliminated full-time DBA position. Actually, my DBA said, I'm bored, I have nothing to do. I offered him a couple of other things to do. He said, I love challenge. So he moved to another company using MySQL. So intangible benefits. reduce the open cost. So increase time spent implementing value added functionality and minimize time spent fixing bottlenecks. And also enable flexible database topologies with other MySQL wire compatible databases and tools. So we use pretty cool solutions like real-time caching validator. So we plugged in MySQL bin log, we read whatever updates going on the master database, on cluster, and then takes certain actions. For instance, if job status changed from active to inactive, we remove it from cache. We use varnish cache in front. So everything happens in real time. So that's pretty much it. Save time and money.
Wait, hang on.
This is a good question. Maintenance. So Clustrix support actually does everything for us. Yep. No, actually 15% of it.
Thank God.
Hang on. Before we start Q&A, I just want to first give a great big round of applause to Sergei Tsarev and we have an Apple TV to give away. To win it, all you have to do is put your data, your card or info into this basket, which please pass around. And we'll do the raffle right at the end of the Q&A. And someone is going home with this Apple TV. All right. Next question. Yes.
Annual, this is Clustrix plug-and-play solutions for your
It's just MySQL right now.
I had a neighbor who did
The architecture allows us to add other kinds of front-end protocols and dialects, but there's so much traction for us in the MySQL market that we're not taking the Close, no. You guys Postgres users?
All the way this one back there. Hypothetical question. So last week there was the MariaDB talk at AppNexus, right? And obviously the founder of MySQL created MariaDB, and he showed that there was a 5 times performance gain just by switching from MySQL to MariaDB. Would there be any performance benefit if you guys were to, I don't know, change whatever it is you guys are doing with this MySQL aspect of your application that would give you more performance to kind of match what MariaDB is providing?
I mean, we're always working on improving single node performance for Clustrix, so every release gets faster for certain kinds of workloads, just like any other database. And we're also adding features. So yeah, but the idea is that, look, your data sets are always going to grow, and having that kind of getting more efficiency in a single node isn't solving the fundamental problem, right? Is that really the answer is scale out.
So really, it's not really a comparable kind of question, right? Because even though the MariaDB is better than MySQL, you guys are just using MySQL kind of as this interfacing kind of layer instead.
Right. We just look like MySQL, but there's no MySQL technology here, so we're not going to take advantage of anything those guys are doing.
Awesome. Okay,
Next question.
So ACID is a hard problem to solve. You guys have solved it on a scalable system. Typically, you have to compromise something in order to have a scalable ACID system, compliant system. Normally, you end up, most of the systems that do actually solve the problem typically do it by adding locking or something along those lines. Performance versus transactional volumes. How are you handling some of the major problems with ACID? Some of them do consistency. Some of them do smooth distribution.
The question
What's
is
the magic sauce?
right.
You guys do it.
The question is ACID, and how can we have our cake and eat it too? Right? It's sort of it's this disbelief. And so really, kind of the answer is that in order to do this, you build a message passing system. You have concurrency models, essentially multi-version concurrency control, so that readers don't interfere with writers, right? I think any modern database system, if you're going to build something, you have to do it multi-version concurrency control is going to fail. And you pay for it in sort of in latency, right? So it's what is your messaging overhead? So for Clustrix, a single write transaction will be slower than a single write transaction against a single instance database. It's just, that's the trade-off. But the real answer is, well, what happens to the database under concurrency? So you're able to scale writes and keep your transaction latencies under a certain threshold. So if you say, okay, well, my threshold for transaction latency is 5 milliseconds, and if you get above that threshold, you can add nodes and keep it at 5 milliseconds. And Clustrix may not go below 5 milliseconds, it's going to stay at 5 milliseconds, but it'll stay there. Right? Whereas with a single instance system,
How many nodes can you guys support?
there's no architectural limitation. You can build clusters up to 64 nodes.
What are you using interface technology? Obviously, it sounds like using InfiniBand to make nodes.
In our appliance, yes, but we also support 10 gig and 10 gig. So it depends on the scale of the problem and how much performance you want out of the system.
And you guys are using the appliance, I presume?
And next question?
I because it was a problem. What is the smallest installations that we have?
What is the smallest installation? It's got to be something in AWS on an M3, M1 largest. That's the smallest. That's the smallest footprint. Yeah, the smallest cluster size is 3 nodes, because you have to be able to lose the node and reprotect the data set and not have a split break problem. We write 2. It's good. When we write 2, at least 2. That's right, at least 2. But you can configure it. So if you have a 32 node cluster, you can say, okay, all 3. No less than 2. That's right.
At the beginning of the talk, you mentioned the load balancing a little more and the load balancing options. Can you just elaborate a little bit on that?
Sure. So the idea is that any node can receive the TCP connection for the actual database connection. So all you really need to is to have a network load balancer. The question is, well, how does the network load balancer know which nodes are actually available in the cluster to participate right now? So we have something that's built on top of Linux IPVS to distribute the load. It usually works up to about 15 nodes, maybe like 80,000 transactions a second kind of load. Beyond that, we recommend switching to a hardware load balancer, and we have a bunch of plugins that allow you to tell the hardware load balancer whether a node is available to take traffic or not.
Next question? That's it? Okay. Throw in, do you have a question?
No. Rising after.
Okay, we are going to now raffle off the Apple TV, if you don't mind. Mix it up, reach in, grab a card, but mix it up good. If you grab your own, you still can win, but you gotta close your eyes. Don't keep feeling, just pick it out. Read it out loud. Ryan Scott. There you go.
Woo!
Yeah, you got it.
All right, thank you guys. I'm going to hang out here a little while longer, have a beer.
Our speakers will be here for one-on-one questions. Thank you both for being